Welcome back to CMOS RF integrated circuits. In today's lecture, we are going to be discussing continuing from where we left off as far as MOS capacitances goes. Then we are then going to talk about further non-idealities in the MOSFET. Then we are going to discuss two important parameters, one is FT, the other is FMAX. So, let us just quick recap. So, we had discussed the MOSFET and a lot of different these are all the different possible capacitors CGS, gate to source, C gate to drain, C gate to body, C source to body, C drain to body and C source to drain, right. Of these we were proceeding one by one. We evaluated C gate to source and gate to drain capacitances, right. These two we evaluated. In addition to what we had evaluated, there will also be a small component called the overlap. So, that is intrinsic to the MOSFET, that is because the gate overlaps with the source a little bit. So, you know the gate is like this and the source comes a little bit underneath. So, this region of overlap causes an overlap capacitance and that cannot be avoided, right. However, you bias the MOSFET, overlap capacitance is going to be there. Okay. So, CGS and CGD and then C gate to body is of concern only when the channel has not yet been formed. You know, you have got a mean depth of the fixed charges and depending on the mean depth of the fixed charges from the gate, you get the gate to body capacitance, right. Now, source to body and drain to body, these are called junction capacitances. I am just going to discuss these. Source to drain capacitance is of no consequence, because source and drain are really far apart. So, I have got the MOSFET, the channel is long, source and drain are far apart. In any case, they are not really separated by a dielectric material, they are separated by a channel which is conducting, right. So, as long as the channel is conducting, you really can't call this a capacitor. I do not see a capacitance here. All right. Now, let us discuss the junction capacitance, that is drain to body and source to body capacitance. Okay. Now, really the drain and the source, these two are made out of N plus type of material, especially when I am talking about an NMOS, and the body is made out of P negative type of material when I am talking about the NMOS. For the PMOS, it is exactly the opposite. We are discussing the NMOS for generality. PMOS you can similarly discuss, identical effects will happen. For the PMOS, you have to remember to connect the body to the most positive voltage in your circuit. So, that the source body and drain body junctions are reverse biased. So, in our case NMOS, we have connected the body to the least potential in our circuit. So, the source body and drain body junctions are reverse biased, the P type is at the least potential. Okay. So, this is what I have got. Now, whenever you have a p-n junction, whether or not you apply any voltage across the junction, you always get a depletion region, right. And so, whenever you have a p-n junction, you get a depletion region across the junction. Depletion region is the region where the majority carriers of the p side, that is the holes, go and recombine with the majority carriers of the n side, right, that is the electrons. So, the holes and electrons diffuse across the junction and recombine with each other, and as a result you are left with nothing in that small region, right. So, there are no carriers in this region. So, it is like a dielectric material, no carriers. So, it is an insulator, insulating material. So, it is exactly like a dielectric, and hence the capacitance between P and N is probably going to be given by this cross sectional area right times epsilon of the material divided by the depletion width. Okay. So, this is the capacitance of the p n junction. Similarly, we have got a p n junction over here, and the capacitance is going to be given by the area of the junction times the epsilon divided by the junction depth. Now, the junction depth of course changes when you apply a voltage. So, right now I have not applied any voltage, junction depth is like this. When I make P a little more positive than N, then what is going to happen? The junction depth is going to shrink, become smaller. Okay. When you make the whole thing conducting, then there is no junction depth. Junction depth disappears when the device is forward biased, when the p n junction is forward biased. So, you can think of it from that perspective. So, the junction keeps shrinking, shrinking, shrinking till they hit each other, and then the device is forward biased, right. That is how the diode works. And similarly, the more you reverse bias it, the more the junction expands. So, when you reverse bias the diode, the junction expands. When you forward bias the diode, the junction shrinks. So, when you forward bias, the capacitance keeps increasing. When you reverse bias, the capacitance keeps decreasing, because the depth increases. All right. Now, ours is reverse biased. The higher you make the source voltage, the higher you make the drain voltage, the more reverse biased it is going to be, and the capacitance is going to decrease further and further. All right. So, that is fine. So, first of all, C source to body, C drain to body are functions of V source to body and V drain to body, right. Basically, you are modulating the width of the junction, the depth of the junction, fine. What else? What is the area of this junction? Now, to think about the area, what you can do is you can approximate, an engineering approximation is to think rectangular. This is the gate. Okay. So, make it look like a box. All right. So, when you make it look like a box, all of these surfaces contribute to the source to body capacitance. All right. So, let us say that this distance is h, the area of the source is A, no, area of the drain is A d, area of the source is A s, the perimeter of the drain is P d, the perimeter of the source is P s. Okay. So, given these circumstances, given these numbers, what is the area of the junction? The area of the junction for the source is going to be A s plus P s times h. Work it out, you will find this is correct. And the area of the junction for the on the drain side is A d plus P d times h. All right. So, what is A d and A s? A d is the area of the. So, if I look in the top view, so this is my gate, this is my source, this is my drain. So, A d I am sorry, A d is the area of the drain, S is the area of the source, P d is the perimeter of the drain, and P s is the perimeter of the source. Okay. So, now you know why these numbers are important when you write your SPICE net list A d, A s, P d and P s. I am sure you have done this, right, and I do not know if you have wondered why these numbers are important. This is why these numbers are important, because they determine the junction capacitance between the source and body and between the drain and body, right. So, C junction source is going to be A s plus P s times h times epsilon of silicon divided by d of the junction. D of the junction is of course, a function of the source to body voltage. If source to body voltage is, if the junction is more forward biased, this D junction is going to become smaller. If the junction is more reverse biased, D junction is going to become larger. That is basically the idea, right. Same formula applies for both source to body and drain to body capacitance. So, these two are called the junction capacitances, right. So, this basically summarizes all the different capacitors in the MOSFET. All right. I have got gate to source because of the channel, I have got gate to source because of overlap, I have got gate to drain because of the channel, I have got gate to drain because of overlap. Usually gate to drain capacitance is going to be much lesser than gate to source capacitance, because the channel is going to be tilted in favor of the source. Hopefully, you are operating beyond pinch off and so on and so forth. So, that you get your current voltage controlled current source characteristics. So, the current is not changing much as you change VDS, right, saturation. So, if you are operating in saturation, typically gate to drain capacitance is going to be much lesser than the gate to source capacitance, fine. Then you have got source to body capacitance, drain to body capacitance. Drain is already at a higher voltage than source, because you are operating in saturation. So, that means that drain to body is going to be even more reverse biased, and that means that drain to body capacitance is going to be substantially lesser than source to body capacitance. Source to body, if you have not increased voltage on the source, if source is at the same potential as body, then you get the nominal junction depth for source to body. All right. Then gate to body is usually not much of concern, because the gate to channel is closer than gate to body, right, and typically the body is devoid of charges anyway. All the fixed charges are usually not going to be present. I mean, it is not going to be modulating, right. So, gate to source, gate to drain is of primary concern. Gate to body, the body is far away. The depth from the gate to the body is significantly more than gate to the channel. However, gate to body is important when we are talking about weak inversion, when the channel has not fully formed. That is when gate to body is really serious. In our course over here, we are hopefully not going to be dealing with MOSFETs in weak inversion. So, gate to body is going to be much smaller than other effects. Okay. Then we have got source to drain. Source and drain are hopefully far away from each other, and there is not going to be any capacitance between source and drain. All right. So, now let us summarize our model. Our model for the MOSFET looks like this. I have got 4 terminals: gate, source, drain and body. All right. And between drain and source, there is a voltage controlled current source. This is the fundamental MOSFET. To account for channel length modulation, there is going to be a large resistor RDS between drain and source. Between gate and source, I have got a capacitance, which is the sum of overlap, which is intrinsic, and CGS, which can be changed with the bias voltages. Similarly, between gate and drain, I have got a capacitance, and then between drain and body, I have got a capacitance, and source and body, I have got a capacitance. I am missing something here, that is the body effect, and body effect is accounted by yet another voltage controlled current source, which is very similar to the original voltage controlled current source. So, we call it GMB times VBS. So, this is the model that we have developed so far. Is this complete? Well, it is not. There are a lot of other things that we are missing out. Number 1, contact resistances. Every time you touch something, let us say I want to touch the gate, I will have to place a contact, and that contact will have its own resistance. So, internally gate, source, drain, body are what where I have drawn, but if I look from the outside world, they are not. Okay. Then there is something called gate resistance. The gate is made out of poly material, and if you think about it, a resistor is also made out of poly material. So, it is like a resistor, right. So, if I touch the gate at the center, let us say I touch the gate at the center, Now, for the charge to reach all over the place, it has to travel through resistive material. Okay. In effect, you could think of the gate as a grid of resistors and corresponding capacitors, right. Now, such a distributed model cannot be accommodated, right, and it kind of depends on how you contact the gate, where you are touching the gate from, etc. So, we typically try to lump all of these distributed RCs together and we put something over here called the gate resistance. All right. Now, in modern processors, the insulating material between the gate and the channel is not really an insulator, it is so thin that charge leaks through. In modern processes like 45 nanometers, 65 nanometer technology, 32 nanometer technology, the material between the gate and the channel, the dioxide layer, silicon dioxide, the layer is so thin that charge leaks across. So, in that case, you can't isolate the gate from the channel, right. Now, this gate resistance that I have noted down over here does not account for that. This is not that, this is something else. This is even if the gate is perfect, just the charge traveling all over the gate and reaching all the different points all over the gate, the charge has to go through resistors. So, that is what this R G is trying to account for. If you want to model further, if you want to model leaking charge across the gate channel boundary, then you have to do more stuff over here. You have to kind of change this model to a BJT kind of model, bipolar junction type of model. Anyway, so that is not what we are talking about here. This is just the gate resistance, because the charge has to travel through the polymaterial. All right. What else are we missing out here? Next most important thing that we are missing out is the fact that electromagnetic news takes time to travel. All right, it is like this. If I say something here, you are not listening to me right now. It is taking a little bit of time for sound to propagate from my mouth all the way to your ears, right. So, the news that I am giving you is taking a little bit of time to travel. The vibrations that I am setting forth are taking time to travel. Similarly, when I apply a voltage at the drain and electrons start moving, the source does not yet know that electrons have started moving at the gate at the drain, or things should be moving. The source is not having that knowledge, or when things start moving at the source, things do not yet start moving at the drain, right. This is what I am talking about when I say that electromagnetic news takes a little bit of time to travel. It travels at the speed of light. Now, speed of light is very large. Our devices might have long channels, might have short channels, I do not know, but we are talking about gigahertz, and when we are talking about gigahertz, the time we have is very small. We have a nanosecond of time, right. So, the fact that electromagnetic news takes a little bit of time to travel is modeled as an inductor in the path of the channel. So, it is like there exists an inductor over there, which tries to continue with the current that was flowing before and slowly allows a build up of current. So, it is not really like this, it is a distributed inductor resistor network. The whole thing is distributed, right. So, the channel is like an inductor resistor, inductor, the channel is like a transmission line. Right. So, if the channel is like a transmission line, we have got to put a transmission line there, we can't just put GM and RDS and so on. All right. So, that is what we have. Now, this is the complete model for the MOSFET, and if we are talking about RF applications, if we are talking about 2 gigahertz, 5 gigahertz, 1 gigahertz, you have to take into account all of these different effects and use them in your model. Small things going wrong here and there can cause problems. Okay. Now, this is the complete model for the MOSFET. Now, we are going to move on to couple of important metrics for the MOSFET. Now, the most important metric, you may or may not have heard of this metric, is the FT. FT is the frequency, the transition frequency. Okay. Now, the definition of the transition frequency is that it is the frequency at which the current gain of the MOSFET is 1. Now, we have something serious over here. What on earth is current gain? Right? What do you mean? What are we talking about over here? So, imagine an experiment like this. Imagine that I bias the MOSFET, but of course, and this is the small signal picture. This is the small signal picture, mind you, not the large signal. Okay. I have connected the source to ground, I have connected drain to a bias voltage such that the MOSFET is saturated, right. Also the gate is connected to a voltage such that the MOSFET is in strong inversion. Let us leave alone the body for now, no need to worry about the body, you can connect the body to the source, be done with it. In the small signal, the drain is at ground because it is at a constant voltage, right. Now, if I push a current into the gate of the MOSFET, how can you push a current into the gate of a MOSFET? Isn't it an open circuit? Well, it is an open circuit at DC, but for higher frequencies you have to think about CGS, CGD and so on and so forth. Right. So, it is not really an open circuit. Okay. So, I am pushing a current into the gate of the MOSFET, and the question is how much current does this MOSFET generate? Okay. And we are going to sweep the frequency of this input current source, it is a small signal current source. We are going to sweep this frequency of the input current source till I out by I in is equal to 1. That frequency is going to be the transition frequency, that is the definition. Okay. So, let us see what the current gain is, and then we will easily find out the transition frequency. So, the MOSFET is going to be replaced by its model. Model for the MOSFET is, first of all, I have got GM, I have got RDS, right. Then I have got C source to body. Is C source to body of any concern? Both sides are at ground, no current is going to flow through it. Similarly, C drain to body, is it of any concern? Both sides are at ground, no current is going to flow through it. Okay. Then I have C gate to source. I have also got C gate to drain, which is going to come in parallel with C gate to source. All right. So, this is the model for my MOSFET. I am throwing out the higher order effects like you have got contact resistance and gate resistance and so on and so forth. Let us not worry about those right now. Those will just add a few more terms here and there. Also the inductance does not really matter. What is going to happen to RDS? Both sides are at ground potential. So, no current is going to flow through RDS. Fine. Okay. Now, I am pushing this current I in. As I am pushing this current I in, a potential is going to develop across the capacitors. Okay. What is the potential that is going to develop across the capacitors? Right. So, V gate to source is I in divided by j omega CGS plus CGD, and once I know VGS, I know GM times VGS, and that is going to give me I out. So, I out by I in is going to be this quantity. So, this is my current gain. Now, when I say that I want to find out the frequency at which the current gain is going to be 1, then that means 1 is equal to G m by j omega C G S plus C G D. Can this really work? I have got a phase problem over here. So, clearly there has got to be a magnitude over here, okay, which means that this is going to be the frequency in radians per second at which the current gain is 1. Okay. Now, notice some things over here. Suppose I increase the width of the MOSFET. If I increase the width of the MOSFET, GM is going to increase proportional to the width of the MOSFET. CGS is also going to increase proportional to the width of the MOSFET. CGS is area times epsilon by D, right, capacitor. Area is proportional to length times width, area equal to length times width. So, CGS is proportional to the width. CGD is also going to be proportional to the width, and therefore, FT is not going to change at all. So, F t is not really going to change at all when I change the width of the MOSFET. What about length of the MOSFET? When I increase the length of the MOSFET, G m is going to decrease, C G S is going to increase proportional to the length. So, F t is going to decrease proportional to length squared. Okay. So, that means that if you want the maximum transition frequency, you have to use the minimum sized devices that a given technology offers. So, suppose you are working at 90 nanometer technology, you have to use the minimum length 90 nanometers. That is going to give you the maximum transition frequency. Now, as you increase length, the transition frequency is going to decrease proportional to L squared, okay, inversely proportional to L squared. Fine. So, this transition frequency is an important metric. The foundry will tell you, or need not tell you, you can easily compute. You just place the model of the MOSFET in simulation and you can easily evaluate the transition frequency. It is an important metric for our RF circuits. All right. The next important metric is called FMAX. FMAX is the maximum frequency at which the power gain of the MOSFET is equal to 1. Okay. So, as you increase in frequency, power gain is going to decrease, and the frequency at which the power gain is equal to 1 is called the maximum frequency. What do I mean? What is this power gain? What do you think is power gain? So, first thing you have got to remember is the law of conservation of energy. Law of conservation of energy tells you that if I put in so much power, then I can put out so much power. The total power that I can put out is going to be equal to the total power that I have put in plus the power that I have wasted. So, if I have got a circuit with some resistors, I input some power, then the output power, there is some output power and there is some power wasted in the resistors as heat, then power in is going to be equal to power out plus power wasted, which means that power out by power in, that is the power gain, is always going to be less than 1. Okay. So, what am I talking about when I say power gain? So, this is very confusing, right? Well, what you have got to remember is that power is coming into the MOSFET from a lot of sources. Power is coming into the MOSFET from the biasing sources, from the signal, right, from the power supply. So, I have got my MOSFET, it is a 3 terminal device. There is power coming in at DC into the drain. Okay. There is power coming in at the high frequency into the gate, right, there is current, there is voltage. So, power is going inside the gate into the gate. At DC, I have got a bias current, I have got a bias voltage. So, clearly I have got VDD by VDD times ID as the input power, right. And at the high frequency, this MOSFET is going to output some power to a load, hopefully, right. So, this total quantity is conserved. The power coming into the MOSFET at the signal frequency, the power coming into the MOSFET at DC, and the power going out of the MOSFET at DC as well as at the high frequency. All of this together is conserved. Some part of the power from DC is converted to the high frequency, and as a result you get something called this power gain, right. Unless you have got gain in terms of power, what is the point in having a MOSFET, what is the point in using the MOSFET at all, right, unless you can have a gain in terms of power at the signal frequency. So, that is what I mean by power gain. So, when we talk about power gain, we have to talk about the small signal model, because really we are assuming that power from DC is coming into the MOSFET and it is getting translated to the high frequency. Okay. So, let me set up my experiment. So, suppose this is my experiment. Okay. Power is coming into the MOSFET. Is there power coming into the MOSFET at all? Is there any current here? Well, there is current, not at DC. At DC there is no power going into the MOSFET. So, we can't really talk about power gain, but at high frequencies there is a current going into the MOSFET. Is that current in phase with the voltage? Well, if you only think about CGS and CGD, if you only think about CGS and CGD, the current is never going to be in phase with the voltage, right. The gate of the MOSFET is going to look capacitive. So, you have also got to think about the gate resistance RG. Okay. The voltage drop across the gate resistance means that some power is burnt on the gate of the MOSFET, which means there is some power going into the MOSFET. All right. This is okay. Then the power output is of course whatever the current is, current squared times RL will give you the output power. All right. So, let us work this out in a little more organized fashion. So, let us apply V in, and we are going to measure the current that is going in. First of all, we have to find out what is the current going in, that will give me the power that is going into the system, and then I have to find out either the voltage at the output or the current at the output. That is going to tell me the power burnt on the load, and finally, that is going to give me my power gain, right. So, instead of starting with V in, why do not I start with pushing a current into the MOSFET? Can I push a current into the MOSFET? I can, right. Okay. So, that quickly gives me what is the power burnt, what is the power going into the MOSFET. The power going into the MOSFET is the voltage drop across R g squared divided by R g, right, or rather I n squared times R g. Okay. Now, what do you think is going to be I out? How do you find out I out? Is there a short procedure? Well, the procedure that I like is by using the Norton equivalent circuit, right. Norton equivalent circuit models the entire system including CDB etc., as a current source in shunt with an output resistance. So, this is going to be the model of the MOSFET etc. Right. And how do you find out the Norton equivalent current? By doing the short circuit test. So, you short out the output and find out what is the short circuit current, and that will give you the Norton equivalent current. So, if I short out the current, it leads me to the previous experiment, frequency at which current gain of the MOSFET is 1. So, that is the experiment I reach, right. I have done this experiment just a few minutes back. So, I know that I out is G m times I n divided by j omega C g s plus C g d. All right. So, this is my current, this is the output current, Norton equivalent current. And what is Z out? Do I need to know Z out? Yes, I need to know Z out. Z out is R d s in parallel with C d b What about C g d etc.? You are going to see the Miller effect, and you are only going to see basically C g d approximately. Right, this is going to be the output impedance. Now, once I have these two, I can easily put R L in shunt and figure out what is going to be the final voltage at the output. And that is going to lead me to the power gain. Is this okay? So, I do V squared by R L, that is going to give me the power at the output divided by power at the input, that is going to give me my power gain. Have I made any mistakes over here? There has got to be a mistake. If I am asking you the question, have I made any mistakes? There has got to be a mistake. There is a big mistake here. Where is the mistake? Well, this experiment of finding the short circuit current is not exactly what I had done before. It is not exactly the same, okay? And that is going to lead me to an erroneous result. The experiment I did before ignored R g. Now, I have got R g over here. Okay. As a result, V G S is going to be different. All right. So, this is going to be the real expression, which means that I in, I out by I in, that is your current gain, I have made a mistake again. Looks like it is correct. I in, no, this is correct. I have got to have made a mistake. Oh, all right. that is my corrected version in fact, which accounts for the presence of the gate resistance. Now, when that is my I out, then things will slightly change over here in my previous computation. All right. Now, why did this affect me? Why was I keen on making this change? The reason why I was keen on making this change is because I am looking for a power gain, right. And if my current is not in phase with the voltage that I have developed, then I do not really get any power gain. So, if my I in over here, I am sorry, if I out over here is going to be something which is not in phase with I in, then I am going to get a serious problem, right. So, that is why I was keen on making this change. All right. So, we will summarize this because we are running a little short of time. So, today what we discussed, we went back to all the different capacitors in the MOSFET, and we primarily discussed the junction capacitance effect, right. The junction capacitance effect is proportional to the area of the source plus the perimeter of the source times the height of the junction of the source, and it is inversely proportional to the depth of the junction. Now, the depth of the junction gets modulated with voltage, that is all you have to remember. Then we developed a complicated model for the MOSFET. We also talked about finite transition time effects, and as a result of that you have to incorporate an inductance in the channel of the MOSFET. And then we talked about two important figures of merit for the MOSFET. One is the transition frequency and the second is the frequency at which I obtain maximum power gain. Now, when you talk about power gain, you have to remember that this is power gain at the signal frequency and it ignores power coming in to the MOSFET at DC. So, with this we are going to close this lecture. Thank you.